Hello. Today we'll be presenting the silicon photomultiplier higher energy radiation detector prepared by electrical and computer engineering students Dominic Hursiak and Brennan Wade, and mechanical engineering students Michelle Chu and Sally Lee. A scintillator-based radiation detection system operates by having a scintillator react with the radiation to produce light. A photomultiplier is then used to detect that light and produce electrical output. Detectors like these exist today in many forms, from handheld to quite large. These devices can range from hundreds to thousands of dollars. It is our goal to provide a cheaper alternative to these devices, achieved by reducing the cost of the light detecting element. Now let's look at the system overview for the actual device. Components will include a scintillator, the silicon photomultiplier, transimpedance amplifier, analog to digital converter, processor, digital display, cooling system, and a housing module to contain everything. With that brief introduction of the components, now let's look into the actual operation of the device. Starting with a radiation source, some form of radiation will enter the device through a window of the housing module. For preliminary testing, a known radiation source will be used to compare to the device output to verify correct operation. This radiation will react with the scintillator, causing it to emit light. The type of scintillator chosen will determine the type of radiation that will be detectable by the device. As of right now, a scintillator reacting to X-ray sources is being considered due to the affordability and the radiation sources available to us. The light emitted from the scintillator will then be captured by the silicon photomultiplier. The silicon photomultiplier is the first step into the control circuit. It's a small chip with a small window at the top. It receives the photons emitted by the scintillator and through breakdown events creates current pulses which are sent to the control circuit. The chip design is limited to 1024 protons received at a given instant, and each breakdown event only lasts about 10 nanoseconds, creating sharp current pulses. Using this specific silicon photomultiplier is the goal of the design, as it is cheaper than the alternatives on the market. Once sent into the circuit, the current pulses need to be conditioned before they can be analyzed. This is where the transimpedance amplifier comes into play. The control circuit has a few stages before a processor can perform data analysis. First, the TIA conditions the raw current pulses. It converts the current pulses into voltage pulses. This is done so the next TIA stage, the accumulator, can work properly. The accumulator is a TIA in parallel with a capacitor, which sums up all the current pulses received over a given period of time. The capacitor adds a memory element to the circuit, making it so the device isn't working at a full load every single time a breakdown incident occurs. Finally, the accumulator signal is sent into the rail-to-rail op-amps, which creates the differential outputs to drive the ADC. Differential outputs are immune to noise and are ideal for driving devices. The ADC is the pivot point between the silicon photomultiplier and the processor. It converts the differential output of the ADC driver into a digital signal for a total of 8 bits of digital data. Each bit will be designed to represent one breakdown event. From the ADC, the digital signal will then be sent to a processor for data analysis. The processor reads the data from the digital bus of the ADC and calculates a measured amount of radiation. From here, the data is finally displayed on some digital output. Through this output, the user will be able to see the measured amount of radiation in real time. A few other components are necessary for circuit operation. A power supply and voltage reference need to be designed to provide 5 volts and 2.5 volt references, and supply enough power for complete device operation. Currently, the device is expected to consume no more than 15 watts. The Peltier cell assembly will provide the cooling needed for the silicon photomultiplier. Although it does not create a lot of heat, the silicon photomultiplier still needs to be cooled down to its optimal temperature of -10 degrees Celsius. Finally, we have the housing of the device itself. This is designed by the mechanical engineering students. It protects the device from the environment and outside light. The housing also allows for swapping the scintillator, so a user can use materials suited for their application. To wrap things up, we'll talk about some of the trade-offs we had to make with these components. The ADC currently has a limited resolution of 8 bits, or 256 pieces of data. This can be a non-issue, or a huge limiting factor, depending on application. More bits will create a finer resolution of the number of breakdown events received and would allow the device to record more precise data. The scintillator itself also has limitations. Each scintillating material is designed to work well in a certain energy range. Currently, the design uses a scintillator that reacts to X-ray sources, but would not react well to radiation below or way above X-ray energy. Various materials also emit different amounts of photons per breakdown event. The control circuit currently has no way to account for different amounts of photons emitted and relating them to the radiation received. These are issues that we will be exploring in later development of the project.